I will begin with a word of prayer. Dear Father, we thank you for this day. Thank you for these students, and I just pray you bless this time, Lord. In your name I pray. Amen. Okay, so I wanted to start by talking about a problem that was put up on the board here by, give credit where credit is due. Who put this up here? Dylan. All right. So the rest of you will thank Dylan for doing this. I believe this is one of your homework problems, yes? So Dylan had kind of a fuzzy idea about how to solve the problem in terms of looking, like his idea was, I can look at s of t squared plus t equal to 3t plus 2, kind of like it's s of 1, 1, 0 equals to 0, 3, 2. And I was like, well, that's a good fuzzy idea, but that doesn't quite make sense, so I'm going to erase it before somebody here actually does that. And but let me just restate the problem. The problem is this. We're given s of t squared plus t equal to 3t plus 2. You're also given that s of t squared minus t is equal to 1. You're given that s of 1 is equal to 0. What you're asked to do is to find formula for s of at squared plus bt plus c. Right? I think this is one of your homework problems. And so, oh, problem 77. I at least should make you guys figure out which one that is, but oh well. So this is problem 77. So I wanted to put on the board two different strategies for solving this problem, all right? So I'm going to erase the purple because, you know, it just doesn't show up well on the camera. Now, so to find a formula for s of at squared plus bt plus c, with the given information, if we know it's linear, we can do that. The reason we can do that is actually that t squared plus t squared minus t, and 1, they actually form a basis for P2. All right? Like you can form a basis for P2 using t squared plus t squared minus t, and 1. All right? And because of that, that's enough information to uniquely define S by the linear extension theorem we talked about. So how do you actually find the formula? There's two different approaches, which are really the same when you get down to the heart of it. The one approach would be just to, okay, so A and B and C are given but arbitrary, all right? So just find the C1 and the C2 and the C3 that make this equality happen. That's a straightforward question of polynomial algebra, right? You can just like equate coefficients and figure it out. I'll do part of it for you. C3 is equal to? I was going to do it. C, yes, C. C3 is equal to C. All right? You can work it out. Like, anyway, I have to leave something for you, okay? So if you work that out, then you could put together the formula by just this argument right there, right? You'd, like I said, this would be C, you know? And these will be, both of these will be some combo of A and B, yeah? Relatively uncomplicated combinations of A and B. And then that would be a formula for S of A t squared plus BT plus C, right? This is the way I tend to attack the problem, all right? But this was not the fuzzy idea that Dylan had. Dylan had a kind of different idea, and I showed him a notation for his idea. So his idea basically was to say, well, I'm going to trade the information that you gave me for a corresponding statement about a matrix, right? And you can do that. So we use the monomial basis t squared t1, right? If you'd like to be edited out of the video, you may make a request. I will do it afterwards. I mean, this kind of video editing is actually kind of amusing and challenging for me. So if you want to make the request, you can. I'm not sure how long it will take me, but I will try. But consider against not doing that, because if you do that, then it'll make the people who, went to CPAC, which is ever so very exciting, have to wait longer to see this exciting video.
Let's also edit Ian into the video, by the way.
Edit what?
Let's edit Ian into the video.
Edit Ian into the video? Ooh. Edit Ian into the video. Now that's a higher form of editing. I'm not sure. That kind of post-production is really beyond my skill set. I don't know. So the first conversation I had with my little brother, he's like, so how you do the YouTube channel? I was like, well, I take the camera to class and the student points the thing at the board, and I have a camera, I have the mic, and we take the mic, because other people do stuff like they'll put a Zoom mic on them or something, and they capture the audio, and then they clap or something, and they sync the audio with the video later. Don't bother with the wireless mic. You can get higher quality audio this way. This is how professionals do it, That's why they always have this thing like action at the start of something, so they can sync the audio that they're taking independent of the video together. I don't do any of that. He's like, so you just take it, and then you have zero post-production, and you just put it on the web. I'm like, yes. At that point, though, I was processing this word he used, post-production. Yes, I don't do that. Whatever that is, I don't do that. So it's very, very, very low tech what I do in here. Anyway, the other way of thinking, so I was just buying some time for you guys to sit down. Anyway, and it should go without saying that I don't take you coming late today personally. Obviously, right? I really don't take you coming late personally any day, honestly. Whatever. Okay, I'm digressing. So, beta is a basis. If we look at s of t squared plus t, it's equal to what? 3t plus 2. So the coordinate vector of 3pt plus 2 is 0, 3, 2. On the flip side of things, this matrix I introduced last time, the matrix of a linear transformation, that times the coordinate vector is equal to the coordinate vector of the output. So like generically speaking, we have the following. We have t of, let's say, v beta is equal to t beta beta times v beta. So this is, if we're just working with a vector, a linear transformation which goes from a vector space to itself, and we're using the same basis in the domain and the codomain, that's the connection between the abstract linear transformation and its matrix and the coordinates. So if I use that, if I use this way of thinking, and I put a t instead of an s, I'm sorry, here, s, right? We're working with s right now. All right. So I'm just using that idea here with the specific data which is given. I don't know this, right? I don't know what the matrix is, but I gain information about it because I'm given these three pieces of data, which when we translate to coordinates and matrix, the coordinates in the matrix, we get this, this, and this. So if you stare at these for a while and you tinker, you can figure out what the matrix S beta beta is. Hey, guess what? I'll tell you the third column. The third column in this matrix is 0. I can see that from this because this is matrix times E3 equals to 0, which says the third column of the matrix is 0, right? I didn't have to break a mental sweat for that one. This says that the sum of the first two columns is this, and the difference of the first two columns is that. So if you think about that, it's pretty easy to figure out what the matrix is. Once you find the matrix, what does it tell you? Your formula. What I'm trying to ask is S of, AT squared plus BT plus C is equal to, how does the matrix help you? Well, specifically, here's how it helps you. You do the inverse coordinate map of the matrix S beta beta times V beta. That would be how we track back once you find the matrix. Hypothetically, I'm ignoring the data that you're given. Suppose that you had a matrix in this situation, S beta beta, which worked out to 1, 2, 3, 4, 5, 6, 7, 8, 9, which is obviously not what we're given, right? Suppose that was the case. What would the formula for the corresponding linear transformation on quadratic polynomials be? So I would do the inverse coordinate map of, and so here my v beta would be what? A, B, C, right? So what is, if I take 1, 2, 3, 4, 5, 6, 7, 8, 9 and multiply by A, B, C, I get what? I get like A plus 2B plus 3C, 4A plus 5B plus 6C, 7A plus 8B plus 9C. And then what's the inverse? What's the inverse coordinate map? So phi beta of AT squared plus BT plus C is ABC. What's phi beta inverse of ABC? It is AT squared plus BT plus C, right? We just, the inverse coordinate map goes the other way. So like the formula in this hypothetical case, it would be something rather awful. A plus 2B plus 3C t squared plus 4A plus 5B plus 6CT plus, why didn't I make this matrix easier? 7A plus 8B plus 9C times 1. So that's how we would track back. If we found the matrix of the linear transformation, that's how we would actually construct the formula for the linear transformation from that matrix. If you come in midstream, you need to watch the video from the start again. It's okay. This should not make sense to you halfway through. Those of you who have been here from the beginning, it wasn't that bad, right? Say yes.
No, it's not that bad.
Thank you. That was very convincing. You're a good liar. I feel like that's much like what I used to have written on the back of my car. I had painted "All generalizations are false" on the back of my Pontiac Grand Am.
90% of statistics are false.
I heard that 86% of statistics are made up. My favorite, though, is the book, like How to Lie with Statistics. The dedication is like dedicated to my wife. How do you take that? I don't know. All right. I'm going to erase this before someone asks a question about it. But okay, fine. Do you have a question about it? Can we start over? I know. We did tape it. It's there. They wouldn't let you leave.
No, they would block me the door. They weren't allowed to leave. Like, I still have to go forward.
Us mountain allows you to meet in a political gathering. Sounds strangely like the USSR.
It's okay. This is not a long-range mic. What was said is does not need to be unsaid. Okay. We must go on. So just a reminder, if we have a vector space V, all right, and basis beta, we have a linear transformation T going over here to a vector space W with basis gamma. And just for the sake of clarity, beta is going to have basis V1 through Vn. Gamma will have basis W1 through Wm. All right. Then we defined last time the matrix of the linear transformation with respect to the beta gamma bases as the following matrix down here. So we do left multiplication by this matrix I'm trying to define or discuss, T beta gamma. Beta is the domain basis, gamma is the range basis, all right? And this linear transformation is defined, there's a couple different ways we can look at it, all right? So, facts. Each one of these facts is either the definition or it is equivalent to the definition, all right? So like it's not something you need to justify. That'd be good if you understood it, but I mean, it'd be good if you understand why these ideas are interrelated, but if you don't right off the top of the, right at the start, it's okay. So first of all, T beta gamma times the coordinate vector of V with respect to the beta basis is equal to the coordinate vector of T of V with respect to, and instead of using V, let me use an X here if you don't mind. I'm going to use an X with respect to the gamma basis. So what this says is that if we go through the lens of the coordinate maps, we can convert an abstract linear transformation into matrix multiplication by this T beta gamma matrix. The abstract linear transformation is not a matrix multiplication to start with, but if we go to the trouble of going through the coordinate maps, we can make it into a matrix multiplication in this sense. But not uniquely so. Like if we pick the different basis for the range or the code or the domain, we get a different matrix. It's not unique like the standard matrix. Like the standard matrix is not up for grabs, right? If you had a transformation on column vectors, the standard matrix is what it is. Here, there's a choice of beta gamma, right? Which is why I will talk to you guys about coordinate change, right? All right, so that's one thing. Another thing is we can just look at T, the mapping T is equal to, so we can write T in terms of these maps. T is actually equal to, so I can go like this and like that again. So the last comes first. The last thing is phi gamma inverse. All right. The next is left multiplication by this matrix. And the first thing is the beta coordinate map. Let me follow that through for you. If we start here, we go phi beta down to here. We go left multiplication by the standard matrix over to there. And then we take the inverse coordinate map back up to here. That is how we get T from its matrix. Conversely, you can take this equation and you can solve for L of T beta gamma. Let me put that over just a little bit because I want to do something else here. I want to write a fairly big equation right here next, okay? So leave yourself a little room. So if we solve that for L of the matrix, what do we got? So these are bijections, which means you can compose with their inverses. Essentially, like you can think about composing this on the right by phi beta inverse, and you compose it on the left by phi gamma. And if we do that, we get phi gamma composed with T composed with phi beta inverse. This formula we can also see in the picture, right? Check it out. To go from here to here, I can first go by the opposite of phi beta up to here. Then I take T to go from V to W. And then I take phi gamma to go back down again. So that's the same as this mapping. This is important because this shows me that I can write the matrix T beta gamma as equal to the standard matrix of phi gamma composed with T composed with phi beta inverse. So on this side, I'm saying the standard matrix of this map. Standard matrix of map from, where is it? From Fn over here to Fm. Now, I'm putting F's here, but honestly, folks, I almost always just ask you about real vector spaces, yeah? So, if you wrote R instead of F here, you'd be right like 99% of the problems I ask you. Okay? So that's the setup. This is essentially just the definition. All right? Let's look at an example. So I want to let T be a mapping from, say, P3, polynomials of order 3, to, let's say, polynomials of order 2. And what is T going to be? T is going to be, T of f of x, we'll let it be the derivative map. All right, so I like to organize my thinking with a picture. So f of x equals to, what's a typical cubic? Something like ax cubed plus bx squared plus cx plus d, right? You guys with me? And then, so there's my v. I'm thinking of v is equal to p3. I take my transformation t, which is the differentiation map. You guys know that one. So t of f of x is what? 3ax squared plus what? 2bx plus c. All right. Great. Now, that's my w, which is P2R. Now, you guys, I'll let you pick the basis for the domain and the codomain. What do you want me to make the basis? I choose the right to reject unnecessarily complicated bases given to me by particularly snarky students. So, like, beta equals to what over here? A basis for P, a basis for,
Or x cubed.
I heard an x cubed, x squared, x1, that's what I was hoping for. What about over here? What basis do you want over here, gamma? Tell you what, this one I'll do 1x, x squared, just to keep it weird. You got choices, right? The order which you put the basis in will reflect the coordinates that come out. Okay, so then I look at phi beta over here. And so, like, what's the coordinate vector with respect to the beta basis of f of x? Well, that is ABCD with our choice of basis, yeah? I mean, the choice you guys made independent of my prompting. And then over here, we have yield gamma coordinate map. Right? And what's the coordinate of the image? T of f of x with respect to the gamma basis gives us what? Would be wrong. It is not 3a, 2b, c. What is it? I heard a c, 2b, 3a. You got to think through it, right? The definition of coordinate is that we'd have to write it as, c times 1 plus 2b times x plus 3a times x squared. It's an ordered basis, and when you order the sum to match the basis, the coefficients are c, 2b, and 3a. That's the coordinate vector. So this is a linear transformation from a 4-dimensional space to a 3-dimensional space. What size should the matrix of the transformation be? 3 by 4, right? And so basically, to get from here to here, we multiply by the matrix I'm trying to find. So what is T beta gamma? I mean, you can play this game, basically. So we're looking for a matrix times A, B, C, D equal to what? Equal to C, 2B, 3A. So what do we get then? What's this matrix? Can you complete the... What? It's a 3 by 4 matrix, right? What is that 3 by 4 matrix? What's the first row? How do I get C? I heard a 0, a 1, and a 0. We have a winner. Would anyone like to play? 0, 2, 0, 0. Very good. And finally, 3, 0. There you go. That is T beta gamma. I've been putting this calculation on every test that I have in this course of this part of the material, and usually 80 or 90% of the students get this right. Once you understand it, it's not that bad, right? Yeah. But it's a good question because it meaningfully involves both linearity of the map, the coordinates, everything's involved here. It's a good calculation for this part of the course. Now, you said one thing you might do here to just tweak my example a little bit, what if instead of putting, I'll make it a separate next example, example 2, if I had T going from P3R to P3R, right, and I just use beta equal to, well, what it was, x cubed, x squared, x1 for both, right? Then if you look at T of ax squared, T of ax cubed plus bx squared plus cx plus d equal to what it was. What was it? 3ax squared plus 2bx plus, plus c, right? Then perhaps you can see that T beta beta is what? So the other way to calculate the matrix of a linear transformation is, well, let me give you a template for how I'm seeing what I'm about to write, okay? You can see that from, so the matrix of T with respect to the beta basis, right, times f of x beta is equal to T of f of x beta. So let's see here. We're trying to figure out what that matrix is. What's the coordinate of the input? A, B, C, D, right? What's the coordinate of the output? So I'll throw you guys a bone here. 0 x cubed, right? So there's a 0, 3a, 2b, 1. Yeah, I meant C. Yes, thank you. I definitely meant C.
So confident about just asking a question.
Yeah, you should question it. All right, so this is what? This is, zeros, apparently. Okay, and then what? Yeah, so, 3, 0, 0, 0. And then 0. I think it's, I need to get a 3a here, so I think so it's 3, 2, 1 on the subdiagonal. Yeah. So here's a question. If I call this, so I'm getting sick of writing this. Let's say that T beta beta is equal to M for matrix, yeah? Is M nilpotent?
Sparse matrices tend to be, though, right?
What's that?
Sparse matrices.
Sparse matrices tend to be nilpotent. Let me ask a different question. Is D, let's say D to the fourth power of D, dx to the fourth, on anything, any cubic polynomial, right? Is this equal to 0? Yeah, I mean, so you differentiate 4 times, you reduce your power down to 0. I mean, everything's gone, right? So if you think about that, t to the fourth acting on f of x should be equal to 0 for all f of x in P3, right? And guess what? We can work it out. That's the next thing I need to tell you guys about. The matrix of t to the fourth with respect to the beta basis is the matrix of t with respect to the beta basis to the fourth power. This is actually an identity, which I'll explain shortly. And so, since we know this is the 0 operator, right? This is the 0 map. If you'll allow me this short manga-style calculation, or I'm sorry, manga style. Anyway, this is the 0 matrix, yeah? Yet, t cubed is not equal to the 0 map, right? Because the third derivative of a cubic polynomial doesn't have to be 0. X cubed differentiates to 6, right? So that will also tell me that the matrix of t raised to the third power is not equal to 0. So I can tell, without even doing any matrix calculations, just looking at the mapping alone and what I know about polynomial differentiation, that that matrix is going to be nilpotent, order 4. And you can calculate it easily, right? If you take m, what happens when you calculate m squared? This subdiagonal is going to shift down. You're going to get something on just the 0 zeros. When you cube it, you'll get something just down in here. And we take the fourth power, that kind of just scoots off the map, and you just got the 0 matrix. So you can check. M to the fourth is 0, but m cubed is not. So this is one thing. There's an interplay between a mapping, which the composition of the map to some power goes to 0, and a nilpotent matrix, right? And the critical theorem is just this. If we have T is a mapping from, let's say, V to W, and if we have S is a mapping from, say, U to V, all right? And let's suppose that, what would that make? Could we compose S and T? Would that make S composed with T make sense? Let's see here. T would, oh no, it would make other way around, right? T composed with S would make sense. See, because S would go from U to V, and then T goes from V to W. So T composed with S would make sense with my given setup. This would be a mapping from where? Yeah, U all the way over to W, right? So, you know, if, let's say beta for V, gamma for W, delta for U, just for the sake of discussion. I'm not following my notes here. My apologies. I've lost my, I had a cheat sheet, but I've lost it. And I tried to print out the notes before class, but CPAC crashed the network, apparently. Sorry. I mean, it could be anything, right? I blame Blackboard. Seems, right? It's got to be Blackboard. It's a communist plot. It must be. It's North Korean operatives, right? Anyway, getting to the point here. So, yeah, no. This is. I have not said. I have only impugned known villains, so it's okay. Delta. Did I just say that Blackboard was a known villain? You guys won't disagree.
No.
Yeah.
Not until we get Google.
None.
Top hat's even worse.
Top Hat is the worst. Yes. Have we done Top Hat? I don't remember. Okay. So anyway, focusing. We'll make up for it some other day. We'll make up for the Top Hat we didn't do today. Don't worry. All right. So going. The matrix of the composite is the product of the matrices composed, but you got to keep track of the bases, right? Like T gets the what? It gets the beta gamma basis, and S gets the delta beta. This is a theorem. And the proof of this theorem, I should probably project for you guys. Let me do that. I hate that we're not getting the coordinate change today, but it's not something that I can rush. Coordinate change is not something that should be rushed. Coordinate change is a difficult topic that, you know, is challenging for a lot of students, so we'll spend a whole day on it. I'm trying to look at coordinate change from the viewpoint of dual space, so that's something else I'm hoping to introduce. So actually the proof of the theorem I just wrote up there, it actually is going to essentially just follow from the corresponding proof for column, for linear transformations of column vectors. Was I taking? Oh, that's right. What the what? Oh, this is hideous. Get away. Ah! All right, go away, you stupid thing. All right, it's here. Now let me just, I'll come back to the one I have on the board in just a second, but just for the sake of full disclosure here. So here, this one, the matrix with respect to, whatever choice of basis you like. If you, oh, thanks, you already did it. Good. If you look at the matrix of a sum or a difference or a scalar multiple, guess what? It's the sum, difference, or scalar multiple of the matrix. The proof of that follows immediately from the formula I have for the, this identity, which is that if we compose the coordinate maps with t plus cs, we have that. But then, what is the matrix of t plus cs? Remember, it's the standard matrix over here, right? So if these identities are true, then I take the standard matrix of this, it's equal to the standard matrix of that, plus the C times the standard matrix of that, and that's exactly the proposition. So I can use this identity I worked out to prove that by relying on the corresponding facts for standard matrices. Now, similarly, the composite rule here, if I look at the left multiplication by the product of these, then we had a theorem that that's the composite of the linear transformations that are formed by multiplying by this or that. But then I can take this and that and convert it to, in terms of S and T, according to the identity I drew on the first board. And these cancel, and you're just left with S composed with T in the middle, sandwiched by these two guys. But that's exactly the multiplication by that matrix. And so that proves that this is equal to this, and if this is equal to that, it follows that these matrices are equal. Because two linear transformations are only equal if their standard matrices are equal. And this is the standard matrix of this transformation, and that is the standard matrix of this transformation. So anyway, it's true, which is wonderful, because then we have other theorems. Like example 12 is pretty much just what I went through with you guys, except I did what? I did the second derivative map, right? And so if you do second derivatives on cubic polynomials, you only need to do 2 of those, and you're already to the 4th derivative. So like the second derivative is nilpotent order 2. As you can see, this matrix, if you square it, it's 0. And yet the matrix is non-zero. So that's a nilpotent order 2 matrix. Now, but this example is actually even more interesting because it says that there's a connection between invertibility of the linear map and invertibility of the matrix of the map. So if I have a linear transformation from a vector space to V to W, and if it has an inverse going from W to V, all right, and if I let beta be the basis for W, and beta be the basis for V, gamma be the basis for W, you know that we have T composed with T inverse as the identity on W, and we have T inverse composed with T as the identity on V. And so you can check that the matrix of the identity transformation is the identity matrix. Well, that's a relief, right? Wouldn't be embarrassing if the identities didn't match up, right? I feel like identity theft or something, but... And then, so the identity of... You guys are easily amused today. That the bar must have been set low in CPAC, I guess. But
It was so bad.
It was bad.
My class was pretty good. It wasn't funny, but he was good.
I wasn't paying attention.
I won't say anything. So id W gamma gamma is also the identity matrix. Anyway, so applying the proposition about the matrix of the composite and multiplying the matrices of the linear transformation composed in the natural way, we have the following. T inverse composed with T beta beta is equal to T inverse gamma beta times T beta gamma. But what does that say? We also know the other way around, that T inverse gamma beta is T beta gamma. So that says that this is I, and that's also I. So it follows that and here's the take-home point, the inverse of the T beta gamma matrix is the matrix of the inverse transformation with respect to the gamma beta basis. This becomes even easier to understand if we use the same basis. If like we're going from a linear transformation from a vector space to itself, then we got like gamma equals to beta, and so it's literally just the statement that the inverse of the matrix of the transformation is the matrix of the inverse transformation with respect to the same basis. Often we have beta equals to gamma in applications. So anyway, there's that. There is a connection between the null space of the matrix and the kernel of the map. So what's going on here, this is a set of column vectors. That is an abstract subspace of an abstract vector space. I mean, it could be a set of polynomials. It could be a set of matrices, whatever. But when you feed it to the coordinate map, it's just a subset of column vectors. So this is how the kernel of the transformation is connected to the null space of the matrix. And likewise, the column space of the matrix is connected to the range through that relation. I wrote a 3-point synopsis of the connection between kernel and null space and the range for a transformation on Rn, right? The difference there was we didn't have to refer to any abstract basis, right? There was no choice of basis that we had to make. Here, you'd get a different null space if you chose a different pair of bases, all right? But there is something that's, not up for grabs. The dimension of the kernel of T is given. Whatever it is, right? If the dimension of the kernel is 3, it doesn't matter what your choice of basis is. This is an isomorphism acting on a 3-dimensional space, which means that this is also a 3-dimensional space. So whatever the size of the kernel is, it's also the same as the size of the null space, and it doesn't matter which choice of basis you pick. So this is somewhat comforting. It says that whatever your choice of basis is, if you calculate the size of the null space of that matrix, that uniquely defines the dimension of the kernel. And likewise, if you pick a basis and you find how big the column space is, that tells you how big the range is in terms of dimension, right? But if you chose a different basis, you'd get a different matrix. And so how do we deal with that? All right? So I think, this is a synopsis of what I just said, which says that the dimension of the kernel is equal to the dimension of the null space of that matrix. The dimension of the range is equal to the dimension of the column space of that matrix. This word rank in nullity is used for both. And the reason it's used for both, even though these are different concepts, is there's no danger of confusion because they're equal. So we can talk unambiguously about the rank or nullity of a map because of this, in terms of the rank or nullity of the underlying matrix. So next up is the concept of a dual space. What on earth is a dual space? Well, what I'm going to break down for you is that we can take the coordinate map and we can deconstruct it into dual vectors. If you have a function of x, y, z, and it's equal to like x squared plus y squared, zy, and then x plus y, these are so-called component functions. Well, they're the formulas for the component functions. You could write f as equal to f1, f2, f3, where f1 and f2 and f3 are the component functions to f. Like specifically f1 of x, y, z is equal to x squared plus y squared. The dual space will give us a way to understand what are the component functions to the coordinate map. We will find a way to take phi beta and break it into component functions. All right, and those component functions will be mapping from the vector space to the real numbers or to the field. That's what a dual vector is. A dual vector is a linear transformation from the vector space to the field. That's what we need to construct the component functions to the coordinate map. So that's why I've put dual space first, because I think it will help demystify the dual space if I explain the connection to the coordinate map. Other times I've taught this, I've just put it off to the very end of the course, and then you guys are just like, ah. So I figured I'd put the here, because you're already about other things. So what's a little bit more, right? No? I'm just kidding. Do your homework, you'll be fine. Anyway, I think that's it for today. Sorry I solved your homework problem for you at the start of class. Sort of.